where path geometry is a geometric tool for studying system of second-order ODEs, like from R to Rn. So I will start from second-order ODEs. So consider a system of the form that assign an initial condition to your desired second-order derivative, and then this system I will call phi, and its domain is R times Rn, which is the jet bundle from the one jet of maps from R to Rn, and I denote it by M, which is a 2n plus 1 dimensional manifold. And notice that the system of second-order ODE is encoded as a line bundle in this one jet, which is the velocity field of any parametrization of the solution curve prolongated into the one jet space. And now we first want to characterize when will a rank 1 distribution encode such kind of system of second-order ODEs, namely of this kind of one distribution. So first, I describe the distribution that is generated by all such one distribution I want to consider. Namely, it's a rank m plus 1 distribution, which you are free in the t direction and free in your x1 direction, and in your x direction is totally determined by how your entry in d by dt is. And second, I describe the subdistribution of this, which I have called the tautological distribution of space where the one distribution representing ODEs cannot lie in. So namely those that vanish in the d by dt slots and hence will vanish in all the x directions as well. And such distribution is exactly the vertical bundle of this of the canonical projection of one jet onto zero jet, which equals R times Rn. And now we can conclude that a distribution encodes a system of second order ODE if and only if it is tangent to the tautological bundle, and it's a splitting of the subbundle of the vertical here. And then actually E typically will automatically have rank 1. And in this case, we say that E is a path geometry on N, or this splitting is a generalized path geometry on the one jet space. And to pass to general definition of path geometries, we need to forget the coordinate of the n. So take n be any n plus 1 dimensional manifold, and accordingly our one jet space has to be replaced by the projectivized tangent bundle, which is a bundle of lines in tangent spaces of n. And remark that the one jet bundle is an open subset of this projectivized if your n is indeed R times Rn. And accordingly, the tautological distribution, again, similarly, will be the tangent vectors on M, which descend to tangent vector in n such that it lies in the line of the base point of your starting tangent vector. And V doesn't change, which is still the vertical bundle of the natural projection. And then a path geometry, as a general definition, is a rank 1 distribution that lies in the tautological and is a splitting of the vertical. And This definition is a formal way of saying that in the manifold n, you assign to each direction on each point a curve with the respecting initial condition. So I list some examples. So first, in the beginning, we show that whenever we have a system of second-order ODEs, the encoded equivalent line distribution is the path geometry. And secondly, whenever you have a path, whenever you have a projective structure, then it induces a path geometry by having the assigned curves being the unparameterized geodesics. And third, consider the path geometry on the space of n+1 dimensional projective space with the assigned curves being the projective lines. And so this path geometry, since the projective lines in the usual coordinates are the affine lines, they are solutions to the second-order ODE of being zero everywhere, however you split your n locally isomorphic. It's the path geometry of the equivalent class of second ODE of x dot equals 0. And this is a homogeneous path geometry because, say, let G equals SLn+2R, and its action on its canonical action on the projective space sends projective lines to projective lines, hence it's an action on the path geometry. And our PTN is identified with flag manifolds of this one, of lines contained in planes in Rn+2. And we choose a base point, R2, then the isotropic group of under the action of G is the block upper diagonal matrices of block size 1, 1n. And with this homogeneous structure, we pass to the Lie algebra levels. And first, we, in the same block size, give a graded decomposition of the Lie algebra of SL n+2. And then you see that the sub-Lie algebra of isotropic group is the non-negative part is the Lie subalgebra of isotropic groups. Hence, we know that on the base point, the tangent space is made isomorphic to the quotient of the quotient vector space of the two Lie algebras. And it's easy also on the base point to see that this G-1e, a one-dimensional vector space, is made isomorphic to your line bundle in this fiber, and the G-1v is a n-dimensional vector space made isomorphic to the v in this fiber, and by the G action on the path geometry, you pass these isomorphisms to other fibers of E and V. And this happens to any path geometry by assigning to it something similar to the homogeneous structure together with something similar to the Maurer-Cartan form. And this assignment allows us to have the same local trivializations of the bundles we are interested in to the same components, which are called parabolic geometry of a type. And the formal definition is as follows. So G SLn+2R as before, and P as before. And the parabolic geometry is a Cartan geometry of the same type. Namely, it consists of a principal P bundle together with a one Lie algebra G valued one form on the bundle such that in each fiber it gives rise to a linear isomorphism, and it maps the fundamental vector fields back to its generator, and it is P equivariant with respect to the principal P action on Tg and the adjoint action of P on the Lie algebra G. And with such properties, these components of Lie algebra will correspond to some vector space in Tg, which further descend and define some rank 1, respectively rank m distributions on M. And we also have that G minus 2, that component will be a trivialization of the quotient bundle of E plus V. And we say that a parabolic geometry is regular if such correspondence is passing the Lie algebra from G minus 1 to G minus 2 to the Levy bracket from the subbundle to the quotient bundle, where the Levy bracket is defined as a Lie bracket on vector fields following the natural projection. And a parabolic geometry is said to be normal if its curvature satisfies some normality conditions. And here I changed, so the regularity definition is the same as the conventional definition of saying that the Cartan curvature has homogeneity greater or equal to 1. So for those who know the parabolic geometry. And then the correspondence we have is as follows. So whenever we have a path geometry, then there is a unique regular normal parabolic geometry of type GP on the projectivized tangents, well, with the base manifold being the projectivized tangent space, such that these this trivialize over this in the way I described in last page. Conversely, if we have a regular normal parabolic geometry of type GP, then there are two claims from the general theory. First is that the underlying V is always involutive if the dimension of M doesn't equal to 5. The second claim is that whenever V is involutive, then your M is, your base manifold is locally embedded into some PTN of some N such that your E and V are embedded into the path geometry of a path geometry on N. So, which can be equivalently phrased as the categorical equivalence between type GP regular normal parabolic and the general path geometries. But we have all the local features of path geometries from the regular normal parabolic geometry of this type. And to work with parabolic geometry, one way is to interpret the Cartan form omega down to the base manifold. This is done by you take the parabolic bundle and quotient it by P plus, where P plus is the strictly block upper subgroup of SL or of P. And then the resulting quotient principal bundle is a frame bundle of this vector bundle or the associated graded bundle. And then a Weyl structure is when you take a lift sections of such a projection. And whenever you have such a section, such a Weyl structure, then the Cartan form pulls back to the frame bundle, hence can be equivalently encoded in terms of objects down in the manifold, namely in terms of splitting of the subbundle E plus V, hence a lift of this quotient back to Tm into a subbundle of Tm, and the Weyl connection is and the principal connection called Weyl connection on the frame bundle, hence linear connection on any associated associated vector bundles, and a 2-tensor field on the manifold. Cartan form is expressed in terms of these. So interpreting Cartan form can be done by trying to give an explicit expression of such underlying data, which is done by what we know about the Cartan form. So one thing we know is that it satisfies the normality condition, and this pins uniquely fix what those underlying informations are. And these underlying information will have might have easier expressions for the reason that part of the Cartan curvature is already 0, so we don't even have to go through the normality progress to build a constraint of the data. And when getting explicit expressions, I can further also restrict to some even nicer Weyl structures by you choose a nowhere vanishing section of the distinguished line bundle E, which will pins a unique Weyl structure whose connection is parallel for this section, and then expressions simplifies drastically, and with this procedure I produce the explicit expression for the underlying data, and this is one of the examples of Cartan connections from direction E on direction V. Others are longer, some are longer and some are shorter. And the explicit Weyl structure underlying information can be used further in another way of trying to understand the information in the parabolic geometry by we equivalently encode it as a tractor bundle together with tractor connection, where the tractor bundle is a line bundle coming from the following way. So the parabolic principal P bundle naturally extend to structure G, structure group G in this way, and then the parabolic form will induce a principal connection here. So whenever you have a G action, then on a vector bundle, then the associated vector bundle comes with a linear connection, and these pair are called a tractor bundle and a tractor connection. And I'm thinking, I was considering the standard action of G on the dual of Rn plus 2. And then this gives rise to the standard co-tractor bundle together with its tractor connection. And to get an explicit formula of an explicit description of how the tractor calculus for this bundle works, I can try to express with the data underlying each Weyl structures as follows. So if you choose a Weyl structure, and I name the underlying information by nabla, the Weyl connection, the row tensor, the 2 field, the 0, 2 tensor field, and the splitting as a lift of the quotient bundle to a subbundle Q of Tm. And then, so the co-tractor bundle, because this principal G bundle naturally reduced to structure group P to the original parabolic bundle, hence your co-tractor bundle comes with a filtration of size n plus 1, n plus 2. And then the choice of Weyl structure will give a direct sum decomposition of rank 1, 1, n, which will also induce this filtration. And the decomposition components are the E10 and this line bundle and this rank M bundle. And we know what E and Q is, where E10 is a density bundle that is a n+2 root of the pullback of top exterior power from on n back to m. So it's like this E10, you tensor it n+2 times, then it's equal to the top exterior power of Tm over V. And for using a next page, I note this downstairs density bundle by E1, which is the root of top exterior power, which also pulls back to the E10, which is this slot of the co-chapter. And then, so you choose a section of the co-chapter, which decompose into 3 slots by your Weyl structure, and then you do the connection on it into the directions of E and V and the lift of the quotient bundle. Then the output is written also in the decomposition and in terms of the underlying Weyl information. Then we can make some observations by using these formulas, but projects to so T star by its filtration projects to rank 1 quotient bundle and also projects to a rank 2 quotient bundle. And projecting to a rank 1 quotient bundle is the same as looking at the first lot of first column of these formulas. And for looking at the first entry of this one, you already see that since projecting to here does not depend on Weyl structures, so we have an invariant operator from sections on V times sections of E10 to section of E10. And also, we can try to see when this equals to 0 is when, for all the directions in V is when it is indeed a pullback of the bundle, the density bundle on N. And then we look at projecting to first slot of the first and the third equalities. Then we see that a necessary condition for our section being parallel for the connection is that it is totally dependent on this rank 1 projective slot. Where is it? Here it is. And collecting our first observation, it should be a pullback. The projective slot should be a pullback section. And then we look at the projection to the rank 2 quotient bundle and insert this section which satisfy the necessary condition of being parallel. Then we see that this maps to here. In particular, here is 0 means this is invariant on the trace of Weyl structures. Hence, we get another invariant operator. And I should stop here.